welcome everyone, and let's begin. Now that the weather has gotten nice and warm, I appreciate you all coming out to nice, warm, friendly McCosh 10 tonight. And I am very pleased to introduce our tonight's speakers. Now, first, before I get any further, if you could please set your pagers, telephones, and other communications devices to a setting that makes us all unaware that you have them, which would be really great. And then I'll start. My name is Sam Wong, and I am former chair of the Committee on Public Lectures here at Princeton University, and I'm appointed to the Department of Molecular Biology and also to the Neuroscience Institute. And it is my special honor tonight to introduce the last public lecture of this year's series, which is Professor Steven Strogatz and Professor Stanislas Dehaene. This is in the ongoing year after year series, the Lewis Clark Von Uxem Lecture Series, which was founded in 1912 by Lewis Clark Von Uxem of the great class of 1879. At least half of the income from this endowment is to be used for lectures of scientific interest. And to just give you a feeling of the breadth and eminence of people who have spoken in this series before, it's included Edwin Hubble, Carl Sagan, Roger Penrose, Lord Robert May, Frank Wilczek, Percy Diakonus, V.S. Ramachandran, and Norel Volkow, who came earlier this term. Mr. Von Uxem himself pursued a career in insurance and specialized in insurance law, but had the foresight to endow this, and he died in 1903. Now tonight, I just want to talk a little bit about our guests and then talk a little bit about the format. First, I'll say the format, which is that this is a sit-down conversation between these two gentlemen who have visited us from near and far away, and they're going to deliver remarks, and then they will sit down and chat for a while, and after that, we will open it up for questions. And so that'll be the way that we're doing things tonight. Now, I'm pleased to introduce Steven Strogatz. He's one of our guests here. He's Jacob Gould Sherman Professor of Applied Mathematics at Cornell University, and he's also Director of the Center for Applied Mathematics. He did his bachelor's in mathematics here at Princeton in 1980, and then he went on to study at Cambridge University and at Harvard University, where he did his PhD. And his awards are too many to mention, so I will just mention a few of them. He's received awards for research, teaching, and public service, and just to name a few, a Presidential Young Investigator Award from the National Science Foundation, and the Communications Award from the Joint Policy Board for Mathematics, which is a Lifetime Achievement Award for the communication of mathematics to the general public. In 2009, he was elected a Fellow of the Society of Industrial and Applied Mathematics for his investigations of small world networks and coupled oscillators, and for outstanding science communication. His research is broad, including biological and physical oscillators, small world networks, including the 6 degrees of separation problem, for which lay consumers of science may know him, and the role of crowd synchronization in the wobbling of London's Millennium Bridge on its opening day. Now, Professor Strogatz is a frequent guest on National Public Radio's Radio Lab, and he also wrote a weekly column on mathematics for the New York Times in the spring of 2010. He also is the principal of a very popular series on chaos, a video lecture course produced by the Teaching Company, and he has also written books. He's written the book Nonlinear Dynamics, and Chaos, and Sync. And his most recent book, The Calculus of Friendship, was published in 2009, and if you're interested in this book, which is based on correspondence between him and his high school calculus teacher, it's available out back afterwards. So that's Professor Strogatz. Now, Professor Dehaene is director of the INSERM Cognitive Neuroimaging Unit and a professor and chair of experimental cognitive psychology at the Collège de France. He comes to us from Paris, somewhat delayed by weather, but he finally made it to us. And he is today a neuroscientist, but earlier in his life, he studied mathematics at the École Normale Supérieure and continued his studies in mathematics, cognitive science, and cognitive neuroscience at University of Paris 6. And I'm sorry, I'm going to do this in English, at the School of High Studies in Social Studies, École des Hautes Études en Sciences Sociales. And his laboratory is now at a very interesting project called Neurospin in Saclay in France. Now, Professor Dehaene is holder of a James S. McDonnell Centennial Fellowship that he was awarded 10 years ago. He is a member of many learned societies, including the French Academy of Sciences, the National Academy of Sciences in the United States. He is a member of the Pontifical Academy of Sciences. He has given several lectures in the Vatican. He is holder of the French National Order of Merit, and his next stop here in America is to be inducted into the American Philosophical Society. He is author of several prize-winning books, which in English are entitled Reading in the Brain, and his Also, earlier before that, he wrote The Number Sense, How the Mind Creates Mathematics, which is related to our theme tonight. And the most recent edition of The Number Sense just was published in the United States this month and has also been turned into a documentary film. Now, I should just say on a personal note that when I was a graduate student, I was very impressed, also as a postdoc, with the work of with both of these gentlemen. And I should say that when I was making a transition from physical sciences into neuroscience, I wanted to know whether it was possible to study things like consciousness or math or reading. And out of France came this guy, Dehaene, who had done these amazing things that I thought were out of the reach of experimental neuroscience. So just speaking as a neuroscientist, I'm very pleased to welcome Professor Dehaene. And as I've said, the 6 degrees of separation problem, of course, is just one of many things that I know Steve Strogatz asked for. Now, tonight their topic is how math comes to mind, intuition, visualization, and teaching. And this is going to be a conversation between a cognitive scientist and a mathematician and many more things. And they're going to exchange ideas about how people learn math and gain intuition about it, whether the mind creates math or discovers it, where math is born in the brain, and perhaps ways to lead students and their parents to embrace math and understand it. So we'll start with remarks from Professor Dehaene, followed by Professor Strogatz.
Well, good evening. Thank you very much for this lovely introduction. I think it's a great privilege to be here. I feel especially humbled because although I did get some of my training in mathematics, it stopped very short. And I did a quite unusual move of moving to psychology and then cognitive neuroscience. So I would like to give a few remarks from this angle of the cognitive neuroscientist who is trying to understand let's say, what are the brain's origins of mathematical knowledge. My laboratory has been involved in doing research on the nature of mathematical intuitions, on the nature of the brain structures and the very existence, in fact, of brain structures that allow us to do mathematics. And maybe we'll get to that later in the discussion, but especially I'm interested in trying to understand whether we can use some of this knowledge to improve mathematical education. Although this is, in all of these domains, I would say these are topics that we're just beginning to understand. Many mathematicians get frustrated when I talk about these topics because what we've been able to study in the lab is not really high-level mathematics at all. It is the simplest concepts that I would argue are essential to mathematics, but some mathematicians think that they are so simple that they're not even part of mathematics. And I'm talking about the sense of number and the ability to do extremely simple things like deciding whether 8 is larger than 5, and I'm talking about the sense of space and knowing, for instance, whether two lines are parallel or what is a right angle and so on and so forth. So bear with me as maybe we'll get to talk about what happens when you go to higher level mathematics, but most of the actual research that we've been doing, for simple reasons of where the field is at the moment, I've been dealing with these very simple objects. And they are not so simple, actually. But so I want to give you, just in this introduction, a few ideas of the kind of research that my lab is doing. The first strong topic that we are investigating is the nature of intuition. I would like to restore to psychology the notion that intuition is an important concept that can be studied. And what we mean by intuition, I think it's, there are several characteristics, but one of them is that it is knowledge whose origins we don't really know, and of which we are not necessarily aware. And we've been doing some research to show that the sense of number is exactly of that sort. The sense of number has now been proven to be available to a broad variety of people and also non-human animal species in a form which seems to be independent of education, such that we can say that the sense of number is, in a certain sense, a given, to the human species before we start educating ourselves by going to school and going to mathematics lessons and so on. And for that, I would just like to refer to you to one experiment that we did. We were extremely lucky to have the chance to collaborate with linguists who are going to the Amazon and who are studying people called the Munduruku. These people live quite far from many of the main cities in the Amazon, although they've been discovered already 250 years ago, so they are not at all, Stone Age people that are not connected to the rest of the world, but they have very little access to education, and they have a language which does not allow them to speak about mathematical concepts, especially in the case of number beyond the number 5. They have number words up to about 5, which is just a word for one hand. We don't know whether it means a handful or a hand. And the other numbers are equally fuzzy. They seem to refer to approximate numbers. They cannot count with them. They cannot recite them like we would say 1, 2, 3, 4, 5. But my research has been involved in purely behaviorally in showing that these people do not lack intuitions at all. So very clearly the sense of number can be dissociated from the language that we use to speak about number. And these people, for instance, the first time they show an example of an addition of two sets, where two sets of dots would go behind the screen, one after the other, and then a third one comes and they have to decide whether that addition is larger than this single number. They were completely able to do these sorts of tasks, even with very large numbers, immediately understanding the situation, what was asked of them, and performing almost at the same level of precision as educated Western subjects. I'd like to tell you of a new experiment we just did recently. It's not published, but I just heard it's going to be published in PNAS in next month, apparently. It's about geometry, and I think it gives us also a sense of this geometry, this sense of intuitions of mathematics in the case of geometry. We wanted to ask these people whether they knew anything about Euclidean geometry and perhaps even about non-Euclidean geometry. And there is, of course, this debate, especially around the writings of Poincaré, whether Euclidean geometry is simpler or more commode, as he would say, more convenient than non-Euclidean geometry. So we took this bold question of asking Amazon Indians whether they knew anything about Euclidean and non-Euclidean geometry in a very simple sense. Now, we showed them a world. We introduced them to a sort of virtual world which they could see on the computer, solar-powered computer, I have to say. But we showed them a sort of flat surface. And we told them it goes forever. It's very, very flat. And this is a land where there are some little villages. The villages are extremely small, so they were, of course, our points. And there are paths between these villages that are always extremely straight. If you go straight in front of you, you can reach another village. So these were the lines, of course. And then once we had introduced that, which took about a few minutes, very much in the sort of Platonic method that Socrates uses in the Meno, for instance. Once we had introduced the situation, we could ask them simple questions. And we asked them, for instance, okay, there are these two villages, so there is a path between them. Here's another village. Could you make a path that's never going to cross the other path from the other two villages? So that's a parallel, of course. And they would say, yes. And then we would ask, well, could you make a second one? And they would say no. And if this one crosses here, can it also cross on the other side? And they would say no, and so on and so forth. And they would get all of the Euclidean answers right. We also asked them this situation where you show them a little village here, and you tell them there is a path here, and it goes to that sort of village, which is here, and here there's another path as well. So there's got to be a third village up here you can't see, but please tell us where it is, and tell us especially how the path would look from that village, and they could tell us with their hands or with a goniometer. We measured that angle, we summed the three angles, and of course it came out, it was very nice actually, 3.14, which is pi, which is, so that in a certain sense they have an intuition that the sum of three angles should be a constant. The story is nice because we can show that they don't always do that, so when we introduce a word which is a sphere, then they change completely their patterns of responding. They know that the lines there should behave differently. They know that the sum of the three angles is not a constant. They make approximations which are close to the spherical triangle, so on and so forth. This is just an example of experiments we can do to show that not all of mathematics depends on education. Of course, we have to agree about the basic concepts like lines and points, but once we agree, everybody has very strong intuitions about these things. And The research has involved a lot of research on babies as well, showing that in the first year of life, babies behave in ways that are consistent with a sense of number. For instance, they will follow also these trajectories of sets of dots, and they will be surprised, for instance, if after putting one set and another set, we drop the screen and there is not approximately the right number behind the screen, and they will show surprise and look longer. So this is the first thing I would like to bring to the discussion. Can we agree that there is a sort of foundation of mathematics, and maybe from the cognitive point of view we can begin to think about the nature of that foundation? And I would like to argue that we have this knowledge because it's been useful in evolution. There is a connection to the physical world. These things, sense of number, sense of space, sense of time, maybe a certain sense of logic, we could discuss that. They arise because they are useful to survival of the species. The second thing is we have been able to describe certain brain structures that are involved. And this is only the very beginning. So I wouldn't want you to come out of this room thinking we know the brain areas that are doing mathematics. It's pretty sure that the whole brain is involved in doing mathematics. But we were able to locate a specific region that has to do with the sense of approximate number. This area will activate whenever any of you in this room compute a simple subtraction. Even one, we can detect it now with a functional magnetic resonance imaging. It's located in the intraparietal sulcus, which is in the back of the head on the top. Here it's bilateral. And what is interesting about this area is that it is activated not only when we deal with symbols, which is quite unique to humans, but also when we deal with these non-symbolic ways of showing numerical calculations, like sets of dots. The story you can read in this new edition of the Number Sense has become very nice with well, we try to think about how neurons in this area, because after all they are the cells who do the computation, how neurons could do this sort of numerical representations. We came up with a scheme where neurons would be tuned to a specific number, and that's exactly what has been discovered afterwards in a monkey, and we think the same scheme applies to humans. So we begin to understand that there are assemblies of cells in this area, each cell preferring a certain particular number. Such there are certain neurons that care about seeing a number 3, for instance. And they will activate in the monkey when the monkey sees 3 objects. They will activate much less if the monkey sees 2 or 4, and they will activate not at all if the monkey sees 1 or 5. So they are completely tuned with a sort of Gaussian tuning curve. And we can explain a lot of the behavior of human subjects by assuming that this is the representation that we use internally to think of approximate number, but in humans we connect it to the symbols. Okay. And this is the second concept I would like to introduce here, is that probably, at least from my point of view, the way we do mathematics has to do with something very special in the human brain, which is the ability to connect symbols with representations that are in fact already present in other species. So in this case it's numbers. We learn to attach particular shapes of Arabic numerals to the corresponding concepts, and in doing so we've been doing research to show what that changes. Of course it changes things, and I will not argue that young babies or uneducated Amazon people have the same sort of concept of number that we have. There is a change that we don't fully understand in the nature of that concept. I can give you some ideas of what changes. The sense of exact number seems to be missing in these people and in other animal species. So for instance, if we ask not about approximation of addition, but about an exact calculation, like 7 objects drop here, 5 come out, you have to predict what will be the exact result, 2 and not 1. Our Amazon people cannot do it, young babies cannot do it, they only are approximate. Okay? And that is a big change that is introduced by the sense of counting, the sense of particular symbols for numbers. Another thing that changes is our sense of how numbers are objects in space. I was extremely interested in my research in this particular concept, and I think it may have a certain exemplary value that we could also discuss. That not only do we have this concept of number, but somehow we map it onto other representations, and in this case it's the number line. The idea that numbers form a certain continuum, and they can be mapped onto lines so we can do measurement. Well, it turns out that this concept is partially intuitive, but not completely, because these people from the Amazon, as well as very young children, they think of the mapping, but they don't think of it as a linear mapping. And they think of it as a logarithmic mapping, which is quite surprising. It does not mean that they understand the mathematical properties of logarithms, but they have a mapping which is such that they will put 3 in the middle of 1 and 9, not 5. Okay? We think this is because of this imprecision of the number system, which means that 3 is just about as similar. But, for instance, 8 is much more similar to 9 than 1 is to 2, initially, with this approximate representation, because of this property of larger variance for larger numbers. So, in the end, we are left with a sort of situation where we have to account both for the existence of very strong intuitions at the beginning, and also for a sense of construction of mathematics. And this is the perspective with which I come to this debate. Or discussion, or whatever. We'll see how it turns out. But I think that we have largely revised the idea that mathematics is just a construction. The constructivist point of view, which is that we really have to build everything from the start, and which I think is guiding a lot of our schooling system, has to be revised, because young children arrive at school with a lot of intuitions. At the same time, the construction process, of course, occurs. And we have to understand how it occurs in the brain, and especially there is a nagging question why it occurs only in the human species. It's got to be something very special in the human species, which allows us to cross these different domains. And I would like to argue that a lot of the mathematics has to do with bridging from one domain to another, and back and forth, and back and forth. And in fact, I'm very humble to mention that I'm giving this lecture in front of Andrew Wiles, who used, I think, exactly these principles of mapping back and forth between different domains of mathematics in order to generate a demonstration of Fermat's last theorem. But we can see this process already right from the start, in a very sense of geometry, measuring the Earth with numbers, and the very notion of measurement is something which is, I believe, a construction, an invention that we've made. I realize that I've been using the word invention. That would be my last word. It really is my point of view that we invent mathematics. It is a cultural construction. We didn't have all of these ideas before. They don't exist in the abstract. They exist because our brains are able to build them and to transmit them across generation, which is what is being done here in Princeton. So this is a definitely non-Platonic point of view, and I'm sure we will perhaps argue about that. Thank you very much for your attention.
I seem to have my own microphone here, so I'll just continue to sit. Thanks for coming out on this hot night. And yeah, I don't know if this will be a debate, but certainly a discussion. I wanted to do something very different. I don't do research about, you know, how people learn math. I'm a teacher and researcher of mathematics. So, but also I, like many of you, was once a student and still think of myself as a student. So I thought I would just give a couple of anecdotes about my own experience learning math, both sort of a very happy anecdote and a very, to me, disturbing anecdote that still gets me riled up when I think about it. So maybe I'll start ranting when I tell that one. So I'll confine myself to those two for now, and then we can start interrogating each other. And also, I think, I don't know, Sam, did you describe the whole format? So we want you to participate too. I think it'll be more fun if you can start asking questions or pontificating or whatever you choose to do. But I think the plan, did you already say? I don't remember. The plan would be for us to talk with each other for a while, but then we also will welcome you. So as far as my two little stories, the first is a story about how I got interested in math, really interested. I mean, as a little kid, I took, of course, I was in school, elementary school. I was subjected to addition and subtraction and all the rest of it. And I liked math, just like I liked the rest of school. But there was a pivotal moment in a high school class where it was geometry. Actually, the course after that. It was a pre-calculus course. And it happened that my pre-calculus teacher, Mr. Johnson, mentioned offhandedly one day that there was a certain geometry problem. That's why I think of it as it wasn't a geometry class, but he mentioned a certain problem having to do with a triangle You remember there's a lot about triangles in geometry class. And so he said there was a certain problem that he had been giving for years, and he had never seen any student solve it. And he himself did not know how to solve it. Now this really, you could imagine, got my attention because I had never heard a teacher say that he or she didn't know how to solve a certain math problem. It was unthinkable. So I, sat up and listened carefully. What's the problem? So he described the problem as one having to do with angle bisectors of a triangle. So if you remember, an angle bisector is a line that starts in the corner of the triangle, goes to the opposite side in such a way that it cuts that angle in half equally. And so the statement is if two angle bisectors of a triangle have the same length, the triangle has to be isosceles. The two sides of the triangle would have to be the same length, or the two angles at the bottom would have to be the same. And so this sounds like a lot of problems you might remember solving in geometry class. There's a lot of them like that. If two such and suches are the same, it has to be an isosceles triangle. So I found it hard to believe that this was really anything that difficult. And the teacher just left it at that. I mean, then he went on with pre-calculus. But I found myself starting to think about it. Why is this? Okay, let me try this problem. And sure enough, it was very hard. I couldn't get it, which I had never experienced before in geometry. Usually with a few hours of work, I could get any problem that they gave in high school geometry. So then I found myself in French class, actually. You may remember, I don't know if you're... That's why I'm not speaking French. Exactly. Because they used to do this thing in French class where there was this kind of ominous feeling as you would go around the room conjugating verbs, and you could feel the train marching toward your seat. And meanwhile, I'm thinking about the angle bisectors, and then it was, I don't know, some plus que parfait or some really tricky thing, and I could never do it. My excuse being the triangle problem. But the same was true in playing JV basketball. Someone would pass me the ball and bounce off my knee because I was off in bisector world. So I don't know, I maybe spent something like, I'd say probably about 6 months thinking about this problem continuously in the shower, on the basketball court, everywhere. Fortunately, I didn't have my driver's license yet. So now what I discovered then, not the solution to the problem yet, but what I discovered was the sensation of doing research. I wouldn't have called it that at the time. I just thought I was working on Mr. Johnson's angle bisector problem. But this is the experience of a mathematician doing research, just thinking about a problem for the fun of it. It's not for extra credit. It's because you love the question, and now the question starts to become an obsession. Those of you, I'm sure can I see who? I don't know who you all are. How many people here think of themselves as mathematical or engineering or scientific people? Lots of you. Wow. Maybe I should ask the compliment question. How many people here, what are you other people doing here? Are the rest of you psychological types, or? All right, I don't know. But anyway, everyone here is, I guess, somewhat interested in math, or they wouldn't be here. So anyway, I thought about this. Eventually, I came up with what I thought was a proof, and I asked Mr. Johnson if I could come over to his house to show him. It was, I felt like I had to show him, and he lived in the town, and he said, yes, you could come over and show me. It was a Sunday morning. He was still there with his little kids. He was in pajamas. I showed him the proof. He's checking it line by line, and he couldn't find any gaps, and he said, you got it, that's a proof, very good. And he was fairly stern. I mean, that was the limit of the praise, but that was enough because it was very, very thrilling to have worked on this and solved it. And those of you who are mathematicians know that this is a well-known problem. I mean, it's a thing called the Steiner-Lemus theorem. It's a hard problem, and there are several proofs known, but that didn't matter. I didn't know them, and neither did Mr. Johnson. And so it felt like genuine mathematical discovery. So after that, I was hooked. I started to make up questions just for the fun of thinking about them, and in that way started to become a baby mathematician. Okay, that's the first story. The second story is I came to Princeton as an undergraduate, and there is a course that I imagine is still offered to freshmen math whiz kids at Princeton, and because every great university has such a course. And this is a course that is designed to separate out the people who are good at math in high school from the people who have actual potential to be mathematicians. You know what I'm talking about? Yeah. This is the course that weeds people out. All right, now we're talking botany. We're talking about people who are going to potentially be viable plants versus people who are weeds. And so I went into this class that is the first course where you learn to do rigorous proofs, because that's what math is really all about at the college and beyond level, is to understand the nature of rigor. And on the first day, it's a linear algebra class. The teacher walked in. We couldn't really tell, the other students, if this was the teacher or a teaching assistant or what, because this person was so shy that he seemed almost invisible. He slithered along the wall, kept his head down, and didn't welcome to Princeton. This is a great thing. You're in this class with all these other smart math students. We're going to have an adventure. None of that. This is a very shy, and I realize now, probably a person somewhere on the autistic spectrum. I mean, you're chuckling, but I don't mean it to be funny. I think this may be something you could enlighten me, or you neuroscientists. That is, I feel like when I go to faculty meetings, there's a significant fraction of the room that is either, has some amount of Asperger's or autism. I know it's funny that the audience thinks this is, I'm kidding. I'm not kidding. That these people are socially, you would say, abnormal and very brilliant in certain ways that work nicely in a math department. Anyway, that wasn't my point. The point was that my teacher had something in this direction, I believe, as an amateur psychologist. Anyway, so he came in, and his first words to us were the words involving the definition at the beginning of linear algebra. A field is, and then he wrote down the definition for a field, and yes, logically, that is how you should begin a linear algebra course. But it didn't work very well for me, and I really suffered in this course. I started for the first time in my life to understand why people hate math, or also not just hate it, but are terrified of it. I used to have this feeling of such disorientation, such a lack of feel for the subject. You spoke about intuition. I had no intuition about what was happening in this course, and when I looked at the book, I noticed there were no pictures. Now, one of the things in our topic description tonight is visualization. And for me, visualization has always been helpful, very helpful, to have a sense of what we're doing here, what am I thinking about. Symbols are great too, but for me, visualization was important. So this book made a particular point of not showing pictures of what was happening, because pictures can lead you astray, pictures are not rigorous, blah, blah, blah. Okay, there's a lot of reasons why a certain stripe of mathematician doesn't like geometry or visual thinking, at least not when being rigorous. Anyway, so I didn't get much either from the teacher or the book, and it was in the end a very demoralizing experience, and especially recognizing that I was being filtered out through this process, that I was one of the weeds. That because I wasn't doing what I was supposed to do as a measure of a good mathematician or a person with potential, the course was working properly. I was going to be left behind. And it makes me really mad to this day to think about that, because why do that? I mean, why teach a course like that? Why put such an inept person teaching such a course when here are all these bright-eyed young students who are in love with math, who really have potential, just so that the department advising numbers are kept manageable, just to help these people from becoming disappointed later on because they really don't have the right stuff. They might as well learn it now. I mean, I really don't know. It's very inhumane, and it disgusts me to think about what happened. Now, you may wonder, how did I become a mathematician after all that? I don't know. Maybe I shouldn't tell you. The answer is Princeton also has great teachers. So it happened my sophomore year. I took a complex analysis course from someone who was very, very inspiring. And at one point when he showed a proof of a certain theorem, famous theorem in complex analysis called Cauchy's theorem, it happened that he drew a triangle. and it seemed like there was not enough information to prove Cauchy's theorem from what he had drawn. But inside that triangle, he drew a smaller triangle, and pretty soon there was this infinite sequence of triangles getting smaller and smaller. And it was very visual and very appealing. And by the time he was done with the proof, crystalline clarity, I erupted into applause. I was the only student clapping. And the teacher looked at me like I was a little bit, maybe on some spectrum of my own. But that course saved me and kept me in the world of math, and eventually I found my way into very visual or applied things, which were probably I was better suited for than abstract algebra. But anyway, so I wanted to raise some of these issues about mathematical education and intuition and visualization from a very personal perspective. Okay, thanks. Is that microphone live?
Because you have that.
I have mine.
Right.
Yeah, I don't want to cause feedback.
So, yeah, wonderful. I have to say I have a very similar experience, actually, of a situation. I was trained for 2 years in the French Grandes Écoles system, which is very similar to what you described. The use of mathematics for selection is quite something quite well known, and exactly the same situation occurred. I was introduced to the notion of connexity in topology by the pure definition, which has to do with overlapping. I don't even know the English word, actually.
Yeah, we don't have the word connexity. Do we have a French mathematician who,
anyways,
what would we call it? Is it compactness?
Oh, no, it means that the thing is one blob together.
One blob, connectedness?
Connectedness, all right. That would be good enough.
All right, yeah.
Anyway,
we might say connectedness.
The definition is purely formal and topological, and I'm sure the teacher had a certain Bourbakist aspect to it, I don't know. Anyways, it took a whole 2 weeks before anyone would help me by saying it's one blob versus two blobs. And then, of course, I began to be much better at it. I am very interested in this from the cognitive point of view, because I think in general we have this bias to think that the more abstract an information is, and certainly mathematics involves a lot of abstraction, the more it involves the frontal lobes where information is being put up hierarchically and involves a sort of construction. And surely that part exists as well. It could be the beginning of the construction of mathematics. There is quite a bit of evidence from young children being scanned in much simpler tasks, of course. But at the beginning of the learning, they always use their frontal lobes enormously, as if to make an act of mental synthesis. But what we see afterwards is a shift towards the more posterior regions of the brain that have to do with space and vision. And I think there might be something quite generic here, which is that as we automatized and we especially visualize or learn the sort of deep meaning, we rely more on this sort of area. So we've done one paper, actually, we were showing that the sense of number in space is reusing, the word I'm using is the term recycling, posterior areas of the brain that are involved in eye movements. Very simple, concrete things. What I think is happening is that in order to have these higher level concepts, we need to reuse part of the brain that were being used for something else which is close enough to the final function. And so in this particular paper, we were showing that whenever you do an addition, you have this little bit of trickling activation to your eye movement circuits. And because it's an addition, it tends to move to larger numbers. You activate as if it was an eye movement to the right. And when it's smaller, when it's a subtraction, you have this little bit of activation on the circuit that will move your eyes to the left. And just after that came this beautiful experiment, which I thought was quite amazing, where you take people, you put them in the dark, you don't tell them that you are measuring their eye movements. In our experiment, the subjects were not moving their eyes, so it was really just activation but not movement. Now, in this other experiment, they place them in the dark, they monitor their eye movements, and they tell them, please generate some random numbers for me, between 1 and 100. And it turns out you can predict which number they're going to give by looking where they move their eyes. If they move to the right, it's going to be a larger number than the previous one. And if they move to the left, it's going to be a smaller number. So it's a very simple example, I think remote a little bit from this higher mathematics, but to show that we recycle brain areas all the way to the back of the brain, actually, in cases where we are dealing with these concepts that are becoming more concrete. And I would think that yes, it's a very good thing to do for education. I would also think that a lot of the bad education has to do with not using this sort of circuitry or not using the kids' intuitions. I am very struck by situations where kids are not able to understand even the simplest concepts sometimes, just because they have the impression that mathematics is disconnected from anything that they know. It's like a formal game. They consider that it's a game that the teacher is playing, but they have no reason to understand the rules. You know, you just have to do what the teacher says. There's one great example of that, and I'll shut up. But I like this example a lot. If you take very young children, like 5 or 6 years old, and you ask them what's 9 plus 2 minus 2, they might just say 9 quite easily. If you take older children, they will do the calculation. Okay, they will do the calculation because they think you have to do like the teacher says.
Yes.
Okay, and they might get it wrong, or in this case, maybe it's too simple. 9 plus 7 minus 7, something like that. All right. So, yeah, I mean, my personal experience as well as these experiments suggest to me that it's the connection to intuition which is really very important. At the same time, of course, you cannot do any mathematics if you don't make this enormous effort to learn the formal aspects of mathematics as well.
Yeah, this question of effort is one that I would like to pick up on too, because what is it that gives a person the incentive to make the effort? Why would anyone make the effort? I mean, it's something I have to think about each day as a teacher, that there isn't really that much I can teach. What really has to happen is if I can imbue a feeling of pleasure in the subject, in the student, they can teach themselves. That's really where it happens. So I always feel like what I'm trying to do is not mess up. That is, if they already like the subject, I want them to like it at least as much after they're through with me, so that they might be motivated to read and think about it. And it feels very personal. I mean, in the two stories I told, I hope the contrast was clear, that by Mr. Johnson's way of doing things, posing a question that became for me very personal, and I could think about it my own way it took a long time. I didn't cover a lot of material. I was just doing one problem for 6 months, but it became my problem, and it was meaningful. And so the effort was there because of ownership or something like that. So I often think that we spend a lot of time, also when academics talk to each other, you know, we spend a lot of time in seminars listening to each other, and very large proportion of those are a waste of time. And it's because we're busy helping someone love the answer. That is, a researcher gets in front of another group of researchers and says, here's this wonderful answer I've found. And the problem is that the listener doesn't understand the question and doesn't love the question. So I think the goal is to help the listener or the student love the question.
But I have a question for you, actually. There are these two views out there. One is that some children just love mathematics and others don't.
Right.
In psychology, it has become known as the spontaneous focusing on number, which is a very abstract jargon to say that some kids, in fact, will very spontaneously deploy their numerical abilities, and others won't, and would be more language-oriented, for instance, same exact situation. But I'm not sure whether this is something that can be changed. Is it part of the individual to love mathematics right from the start, or is it something that could be inculcated to any child because the field is lovable if you just present it right?
This is a good question, and I'm sure there are people here who have empirical knowledge about it. I don't. I mean, only just a sampling of my own. I would like to say everyone could love math.
I agree, actually.
In my heart, I don't think I really believe it. I don't know. I'm not sure what to think. I'm not fixed on this. I don't know. I think most people could love math more than they do. I mean, but anyone who's encountered real talent, you know, as a teacher or in the company of our friends, obviously there's a distribution of something like native ability, whatever that means. But I don't think that's so important because most people don't even come close to reaching their ability or passion for the subject. So
my personal feeling is that the passion, well, first is an essential ingredient, and you're absolutely right to mention that. There is a great deal of change in cognitive science in the past 20 years that is now fully considering the emotions as part of the cognitive apparatus in a full sense of the term. So that there is only a computation of the emotions, which is absolutely fundamental. It's not a separate system. And of course, Antonio Damasio has popularized this idea, but it's become much more precise now, with the sense that emotions are contributing to the very algorithm that allows us to learn. So it's part of the learning system. But in the case of mathematics, I have the feeling, which is not a demonstration, that what can be done to change mathematical education is to introduce lovable problems. Things that are of a certain nature that any child's curiosity is going to be aroused by them.
Well,
that these things actually exist in mathematics.
So the question, I mean, lovability, I agree. I'm not sure lovable problems is the way, because some people may love history of math. That is, they might love the stories and get interested in the human element. Some might love, some may love puzzles. There are many things to love. So I sort of feel like people are. There's a lot of different buttons that can be pressed, and to just approach it one way, that is, everyone should love puzzles, I think you will miss a big fraction of the population. I don't know, it feels like that there are many different things to do. So for instance, I told the story in terms of my working by myself for 6 months, and that's in, popular stereotype is the mathematician working by him or herself, but actually math is very social. Practicing mathematicians, that sounds like practicing Catholics or something. But anyway, practicing mathematicians spend a lot of time being stuck together. Someone will say, I'm stuck on this, and they'll stand at the board or nowadays at a computer and talk a lot and be stuck together or go for walks. And it's very, very helpful to be with other mathematicians. I think we're among the most social of all academics for that reason. So it's not something you normally hear. It's not the stereotype, but that's why conferences are so important for us, or having instructorships. We have young postdocs, that come. It's very rejuvenating for everybody to have conversations. And also when you're stuck, there's no one else who can understand what it's like except for another stuck mathematician. Anyway, I mean, my point there is that educationally, as far as puzzles, it may be that group work for some people would be very motivating, the feeling of working and being stuck together or solving something as a team. I myself always hated working in a team in school. I found it very confusing what other people were confused by. I didn't want their confusions on top of mine. But other people seem to thrive on that. So I would like a very ecumenical approach of trying lots of different things to activate different kinds of people. Did you want to jump in at some point, Sam?
I did. I think I can't help it as a neuroscientist. I wanted to just stir the pot a little bit with the both of you. So one thing I was very struck by is this talking back and forth about problems being lovable. And Steve, in one of your stories, you made a joke about your colleagues perhaps having a little touch of autism spectrum disorder.
Yeah.
And I wanted to...
It's not a joke.
It's not a joke. And I wanted to explore that a little bit. So the relationship between subject matter interests and other kinds of neuropsychiatric and other problems that in their extreme become non-functional. So there's work by Simon Baron-Cohen that has demonstrated, and others has demonstrated pretty well, relationships between neuropsychiatric disorders in the extreme cases and then subject matter specificity, right, interests in non-clinical people. So for instance, I've surveyed the Princeton freshman class, the class of 2014, and I found something very similar to that result, which is that math and science majors are 3 times as likely to have autistic siblings as those in non-technical disciplines. And since we know that autism is a neurodevelopmental disorder with a very strong genetic component, it implies that there are genetic factors that drive our subject matter interests. And there are also reports of something else, which is in humanists. Humanists are more often more likely than non-humanists to have siblings with mood disorders. And so I wanted to get, it's true, bipolar, mood disorder, depression. And that's something that also appears again in students, in college students, who are who are very highly functional students. So I wanted to get back to the lovability problem, right? Lovable problems. I wanted to ask you about the teaching of math. If you encounter someone who's in this other sphere who does not find a problem lovable the way that you do, and evidently finds other things lovable, so how can you imagine making a math problem lovable to someone who doesn't love it the way you do? Is that a bridge too far?
Would you like to go? You want me to try?
I don't know. In the lab, we study such simpler mathematics, but we would like to try to address this problem of why some kids get not even started at the basics of mathematics, which is calculation and number understanding. And there are some children with dyscalculia who are being described as having a very specific deficit, similar to dyslexia, but in the domain of calculation. I've seen a few of these children, and in a certain sense, quite interestingly, actually, they are similar to what could happen to any of us in this room if we had a lesion in this intraparietal sulcus. Some of these patients I've seen after an accident in this region lose the ability to understand the number line, to understand something as simple as what's 7 minus 2, or what's between 3 and 5, this sort of orientation in the number space, okay? And we think that it's not, in the case of developmental dyscalculic at least, it's not a completely hopeless situation, because it's a developing brain with a lot of redundancy and plasticity. And so the hope has been that we can, first of all, detect these children very early. I think that's very important. Second, not stigmatize them so that the emotions do not get in the way. And third, get them to practice and in a playful situation. So that's what we're trying to develop, but I realize it's in a very simple situation. We have actually developed in the lab a computer game which is being used by children with dyscalculia or just who are at risk of dyscalculia. And there is beautiful research by Bob Ziegler, actually in Carnegie Mellon, showing that it's enough to play board games to enhance the sense of number and of the number space in this sort of children, and in fact in all children. It's perhaps something that is also responsible for the social gap in mathematics, which is huge, because of course in many families in this environment, people will play these sort of games, but they might not do so in more poor neighborhoods. So I'm mentioning that because I think these are extraordinary concrete examples where we can make elementary mathematics lovable because it's part of a game. And it's part of a reinforcing situation, and even if you lose the game, you are having fun. And I don't see why this sort of approach cannot be pursued, of course, with a greater degree of seriousness, but at the higher levels. I think when you talk to mathematicians, they describe how fun their work is,
yes,
how interesting it is, I am very surprised by this transition that occurs in the children when they move from this young age where they are outgoing and extremely curious about all of these facts of nature and science, and maybe at the age of 9 or 10 suddenly we lose this momentum. I think the way to keep it is to manage the positive emotions and the game aspect of mathematics.
That sounds right. There may be some real teachers out there who have worked with these populations who could tell us why that's not practical. But I would like to believe what you're saying, that certainly the experience of mathematicians is that it is playful to do our subject. And it is fun, even when you're stuck. This pressure to always be right. You know, in school, you get penalized for being wrong. And that's very inhibiting. I mean, yes?
Yeah, like the dichotomy between right and wrong answers, and yet Stanislas was talking about the sense of approximate number as being a thing that people have intrinsically. So for instance, the ability to facility with approximate number in childhood is strongly predictive of mathematical ability numerical.
Yeah, that's one of the interesting discoveries lately, is that both the integrity of this region in parietal lobe and the corresponding psychophysical measures that we can have of how precise you are in, for instance, discriminating a set of 10 versus a set of 12 or 13 or 14 objects. How much do you need a difference in order to decide that it's a different number? That precision predicts, in fact, your scores in mathematics at school, and it predicts them even at a long temporal gap. So it has a very good predictive power. We don't fully know the direction. I mean, it's a correlation. So it's very clear that there could be effects in both directions. You can enhance your sense of number by practicing number tasks. But it seems to work also in the causal direction, that if you have a refined sense of number, you're likely to have better intuitions that will work out in a school context. So yes, that's one of the important pieces of data that makes this connection between this early understanding and the later development at school. Yeah.
Should children play games that build their intuitions about geometry and number? Is that, I mean, to get away from the stigma of exact answers and to build those intuitions?
I don't have an answer for that. We still have to think of the right games, I suppose, that would teach mathematics. A lot of the art is there, I think, in providing the right environment that will be conducive to mathematics. And I can only speculate at this point that, of course, there are a lot of activities that primarily, I would suppose, boys have been playing. I don't know about the sex differences and whether we'll get to that, but that involve construction games and design and measurement and model building and so on and so forth, that are all activities that, if you think about it, are practicing these foundational aspects of mathematics, although they are not considered at all as being mathematics, but they might involve the sort of intuitive demonstrations that you were talking about.
So the classroom manager side of me feels like you've all been patient and we should let the audience start. There's a hand firing right up.
First of all, I want to comment on the story about the kids in the math department. My own freshman experience. I can only hope if they're math that the department has broadened its understanding of its
Sorry, maybe since you don't have a mic, are people able to hear?
Yes,
yes, okay, then.
Quite audible. Maybe later questioners could, if you're willing, to stand up so we can make sure that it's easy.
because of a relatively new learning disability. Left and the right side of the brain are highly differential, right? The left side being very high and the right side being very low. And the prediction there is that such students would not have much talent for math. And I'm wondering if you could comment on how vital parity or the gross differential between both sides of the brain might have impact.
Well, this notion of the two sides of the brain is being under heavy revision these days, with the finding that a lot of the functions are extremely bilaterally distributed. It's really a sort of caricature to think of some functions as left and right. So, for instance, these quantity functions that we're talking about are completely bilateral in terms of activation. Now, it's true that in terms of lesion, it's essentially the lesions in the left hemisphere that will create this sense of dyscalculia. And that may be because it's creating especially a disconnection with the language functions, which are in most people, not in all people, but in most lateralized to the left hemisphere. But even for language, when you look at it from the fMRI point of view, from the brain activation point of view, it tends to be strongly bilateral activations with the left shift, with the left emphasis. So, yeah, no, I don't want to just say bluntly like that the whole brain is involved in mathematics. What I meant is that there are many specific representations. And that mathematics seems to me to involve a lot of these different representations. In fact, I'm very struck by the fact that new areas of mathematics seems to emerge when people think of a new property that they can exploit, which becomes mathematical. Like the theory of knots, perhaps, is an interesting example. A fairly recent evolution, which starts with something which is quite intuitive to many of us, but was not yet put into a mathematical formalism. So I would like to think that there are areas of the brain, and many of them actually, that are involved in the sense of space, both navigation and how objects are being oriented identity space, which was Poincaré's strong starting point of view to think about invariance. There are other areas that are involved in number. There is a strong sense of time in the brain, which involves different areas, in particular in the basal ganglia. And it is in that sense that I meant that mathematics involves different aspects of the brain. How we put it all together and create this crosstalk between areas, that involves more distributed regions, in particular of the frontal lobes. So that I hope that clarifies a little bit what I was meaning.
There's a question all the way in the back. All the way in the back.
I have a question. The question is math more art than science? And the reason for that is that I'm not artistic, I'm not musical, I don't know. So, but I happen to love math. But somehow I'm not really that good at it. I can't compete with Princeton professors, I'm really mediocre. And it took me a long time to sort of realize that maybe there is something, math is not really just, it's not what we call science, it is artistic. Man, to take Asher, for instance, who didn't know any math, but his geometry in his drawings is extremely sophisticated.
Yes, it's a very interesting question. How would we classify math as, you know, is it art, is it science? And we've talked about so many different dimensions of it already tonight because it has an aspect of a game. Certainly it can be a sport, people competing. My tendency would be to resist. I think of it as math. It's got all these different aspects. Now, that's not a good answer. So, let's say it has a lot in common with art because you can express yourself through math. You have obviously lots of room for imagination, which you have in art. There's definitely an aesthetic notion in math. Not everyone agrees what is a beautiful or elegant proof. But almost all mathematicians, I mean, while they might disagree about whether this proof is more elegant than that, all of us are interested in elegance. And I mean, I don't know anyone who likes ugly. I suppose there are probably some who don't mind ugly math as long as it's true. That is, they will settle for an ugly proof as long as they have a proof. So, on the other hand, I feel like art is more free in that there are certain constraints within math that I don't associate with art. Now, maybe I'm naive about art. I am, but that is, in math, when you invent certain concepts, so I would agree that concepts may be invented, but the results are not invented. That is, having made certain definitions and agreeing that we're going to use standard logic, the answer is there. And that part I don't feel is true in art. You know, I mean, is that obvious? That different composers will there's no inevitability about a musical composition or a painting in the same way that there is about a mathematical result given certain axioms, and you know what I mean. So it's less than art in a way, but it's also more than art because it tells us things to a very good approximation about reality as it really is. I mean, it's got aspects of science. These concepts that we invent obey laws, sort of like the real world obeys laws, except in a more perfect way than the real world does. So it's got a bit of art and science and everything else in it.
So can I ask you about this sense of a boundary or a certain something really hard in mathematics in front of you, that is, you have this feeling that there is only one possibility, or this reality exists out there, right? Is this something that you think that, I'm sorry, I'm not expressing myself very well, but do you think that these mathematical objects have an external reality that is imposed on you, and there is no way you can turn around it? It's there in front of you, as real as any, say, maze is, in a certain sense. It's a hard wall. Or do you think that it is a creation of the brain?
Well, right, so this is a great problem that a lot of us worry about. How much is math out there, or is it just in our minds? And I will just speak personally. I think, though, a lot of mathematicians, if not most, would agree with me that it feels like it's out there. I'm not talking now about the real world. I'm not talking about how math connects to physics. I'm talking about, for instance, something like there's a famous unsolved problem, maybe the greatest unsolved problem, that we call the Riemann hypothesis. And it asserts that certain numbers the so-called zeros of the Riemann zeta function, except for certain ones that are called trivial that we disparage and don't worry about. We already understand those. But the non-trivial zeros all supposedly lie on a certain line. And no one knows if this is true. And we think it's likely to be, well, I think most people would, that most mathematicians would say it probably is true, but we don't know. And to me, and I think to most of us, the answer doesn't care what we think. The answer is out there. The Riemann hypothesis is either true or it's not. I suppose a logician could tell me it could be undecidable. And I don't know what the status of the question is in that respect. Does someone know?
That wouldn't affect whether it's true.
Aha.
It would just affect whether you can prove it.
Yeah.
Oh, well. This is a deeper part of, so say that again?
The undecidability of the problem wouldn't affect whether or not it's true.
Yeah.
It's whether or not.
This gets into the deep question of are the true things provable or not? We know that some truth, you're claiming that there could be things that are true but not provable. That's one of Gödel's implications. Yeah, so now we don't know if this might be one of those. Right? That's open.
Well, we're getting into very interesting territory there.
These guys are playing. This is the element of play, right? You're playing with the ideas.
Leaving aside the question of whether it's undecidable, let's say something easier, like adding two odd numbers to get an even number. Okay, we know that if we add two odd numbers, it will produce an even number. A little child might not know that and might not know the proof. But the truth of that statement is out there. So it's not something we've invented.
We can argue that we all agree about the truth of that statement.
We do agree,
and
right?
I think we will argue. I will argue that it's true that it seems to you that there is a reality out there.
A mathematical reality.
Because I think that's how most mathematicians feel about it. But it still could be a creation of the brain. And the way I would like to play this is that there are many instances in the history of mathematics where what seemed to be impossible hurdles were actually crossed. Because we changed our mind about how we should think about this object. So you think of all of these things that were called irrational, imaginary, because people could not get their minds around them, you know? And they thought they were a hard wall. Or I'm thinking another example apparently was people had a lot of debates about the sum of the series +1, -1, +1, -1.
Very good, yes.
And I think, it was a great mathematician, I don't remember now, who came up with a solution. It was 1/2.
Leibniz and Euler both thought that.
Wrong, right?
No.
No?
In a certain sense, that's the right answer.
So maybe that's the right answer, because it's some definition. The point is that, and that's, I think this was the point somewhere here in the room, is that it partially depends on how you define these objects. Once we have a sort of social agreement about what are the objects and what are the rules. No, I really want to use it in the normal sense of the term.
Okay.
You mathematicians agree about the rules of the game, and then you have a feeling that there is a strong reality. But that's after you've agreed about the rules of the game.
Yes.
Let's try for a few more questions here. Just you and then you.
Go ahead. You choose, Sam.
You and then you.
School math and science teacher.
Very good. Thank you for your service.
I undoubtedly taught some of the children of the parents in this room, but I would just want to comment one on motivation. As I said, I see a whole bunch of very strong students, and some are motivated by the competition. They come to life if they can do a little better in math than somebody else. It's a game. There are others who are your basic good students. They want to please the teacher. They want to please their parents or whatever. And they're also good students. There is a tiny number of extraordinary students who are so intrigued by the thing itself that even if they're not at the moment as facile as some of the other students, I think are far more likely to become serious mathematicians. The rest of them will always be able to use mathematics. They're more likely to end up in science using it. Now, I come to my question, which is the explosion of electronic media, net plus or minus for math. And what I have in mind is one specific thing, and that we recently invented a new version of Monopoly. I would call it Monopoly for morons, in which we no longer have to count or make change or do any of the mathematical tasks that we associate with Monopoly. So.
So if I understand the question, it's whether having technology, now that everyone has a computer, well, not everyone, many people can get online and stuff. Is that a net plus or minus for math? Math literacy or math numeracy or something? Would you like to weigh in?
I don't know. I just always point out the fact that technology is in part creating a movement forward in math. I mean, we don't realize, but Arabic numerals are technology. They are an invention. They are a wonderful invention, but it took a lot of time before it was accepted. The normal mathematics before that, like in the Roman times, was done with called a dustboard or an abacus, and it took some time before that new technology was adopted. It's the same with the calculator, I think. We shouldn't be shy about the calculator. It's extremely good technology to supplement what our brains don't do very well. But the whole history of mathematics has been inventing notations and technologies that are useful shortcuts to supplement the deficiencies of our brains, to make us able to think better about these things. So the calculator can be used in this sense. It can, like we all use it to save time, to not do long division, these sorts of things, but this time can be used to enrich the kids' intuitions. I have 3 boys and I gave them all calculators as toys, actually, and they loved them as toys because they could do all sorts of fun stuff with them that actually creates a sense of what is magic about numbers, right? So that's how we use a calculator. Actually.
You had your hand up a few times. So. Somebody will repeat the question.
Okay.
So you mentioned some people.
Do you want to repeat it, Sam, or you want me to try?
So I guess one question is like overlap in brain mechanisms behind math ability and language ability. Another question is whether capacities such as having Chinese as a native language can underlie better scaffolding upon which math can be built.
How, like you were saying in the beginning, how is it related to reading? Because, for example, for Western people, read from the left to right.
Yeah. That's totally related to reading. It's a cultural direction. At least in people who, if you make everything else equal, there is a component of reading direction. Yeah, very important. Of course, now the convention is math is always left for small numbers and right for large numbers, even in countries that are right from right to left. So it's difficult to test. But if you isolate the reading component, you can show it's an effect of reading. Now, the big question about language and math, and there is an even bigger question in psychology, of course, with the relation between language and thinking. I think the number case is a wonderful example to show that there can be enormous level of deep conceptual thinking without language. And I always use it to demonstrate that. At the same time, it is a case where the use of linguistic symbol is enriching considerably what you can do in the sense of exact calculation. And we have this basic division where some of the mathematical facts are stored in a linguistic form and others are not. This plays very beautifully, if I may say so, in the case of brain lesion, where you have some people that lose specifically the more language-based aspects of mathematics, such as it's barely mathematics, but for instance, I have seen some patients who have lost their multiplication tables, but can still do addition, subtraction, okay? And the converse is true as well. You can find patients who have trouble subtracting, but can still multiply. That's because multiplication seems to be largely stored verbally, as a table, whereas subtraction usually is done by playing with the quantities in your mind. we're having trouble finding much deep mathematics that has to do with language. The research is on at the moment for algebra. It's just starting, but people are asking this question, which can be related to some of Chomsky's earlier statements. There is a single recursive system in the human brain, and maybe it's being used both for algebra and for language. And the finding is now that there is remarkably little overlap between the brain areas that we are using to do even complex algebra and those that are involved in processing the structures of language. This is quite a surprising finding, but it's coming out of several different labs now. It may not be the end of the story, but it does suggest quite a bit of independence, at least for the important conceptual structures of mathematics. We seem to use language as a scaffold in many cases, especially for memory. And I close with that. That seems to be what's happening in the Chinese students, that language in the Asian countries is simpler to name numbers. And there is this wonderfully simple situation where instead of having 10 numbers, you have, you say 10-1 instead of 11, you say 10-2 instead of 12, and when you reach a decade, you say 2-10 instead of 20, and 2-10-1, and so on and so forth. So it's a wonderfully simpler system. You can show that there is a 2 years advantage in counting and simple knowledge of counting just due to that, which is the simpler rules that are involved in the Asian countries. It's not a deep conceptual idea, but it has consequences for the speed with which and the efficiency with which we can manipulate number. And I think mathematics has a lot to do with that, finding the right formulations, the right notations that are compact enough for our brains.
I'm a little concerned about the time here, and I think I saw a practicing mathematician in the front row getting ready to ask a question. No, you're over it, John? Oh, John Conway had his hand up, but okay. But perhaps, let's see, so the last question. I mean, people are welcome to stay around, but I think we have to have a time when people are allowed to leave without embarrassment. So, so why don't we take another question and then sort of compress our group.
Sure.
Thank you. I'm an historian. I've never ever been to a lecture on after at Princeton, although I've always been fascinated by this question of coverage. So, and I can see that the jury is out on that. So, so I want to ask specifically about that. I wanted to ask a question of but when it gets to school, you know, you have to get educated to get a more
I'm happy with the term quantity, actually. I think that's correct. What you have to put behind that term, though, is a sense of invariance. And again, this concept is crucial in mathematics. We can show that the concept that young children and these uneducated adults are bringing in the field is a real sense of the invariance of number. So they know the commonality between a spoken, between an auditory sequence of tones, for instance, and the corresponding set of objects. There's a beautiful experiment that does this now in the first day of life. That's absolutely amazing. That's published just a few months ago by Véronique Izard, where babies are exposed to sets of 3 objects or 2 objects, and at the same time they hear 3 tones or they hear 2 tones, and you can show by the behavior of the babies that they are attuned to the correspondence between the tones and the object. So it is, I'm happy with the sense quantity, but you have to realize that it's a pretty abstract notion.
Right, but that would, does that, or am I getting this wrong, does that touch on this question of whether math is out here or in our heads? Because I think quantities are out there, but the number 3.
Right, we would all agree with that. 3 has been made up.
Well, if you agree with that...
No,
I think we agree.
No, 3 has been made up, but 3 plus 3 is determined once we've made up what 3 is.
So God made the integers, I thought. But,
okay, if you want a formula. No, I mean, the point is that math is both. I mean, as far as your question, is it created or discovered? It's both. We create some of it, and then we discover the rest of it. That's what it looks like to me. I mean, maybe it's to to an easy way out. But obviously we're creating certain notions, but then the theorems, I sure feel like we're discovering them. We're not...
I think it's
Once
exactly
the
like the
concepts
game
are
of...
created, they're being discovered. How could anyone not think that?
So once, I'm sorry, John, did you want to, okay, one.
I'm going to try and rephrase the point that Stan made earlier in response, which is that a train thinks that the only paths through the world are its tracks. And so if our brains are constructed so that once you make up 3, the only thing, and you make up plus, the only thing you can do is come up with 3 + 3 = 6.
Yeah.
That's a form of, potentially, I'm not saying it's necessarily, but it's potentially a form of a track. Right? It could be determined by the wiring of the brain that you're constrained. Now you have to ask, well, does that mean that it's out there or not? But from that point of view, it's out there, possibly constrained only by the wiring of the brain rather than anything sort of epistemologically universal.
Okay, so, all right. So, you know, with that...
I don't know, I got nothing.
Excellent rejoinder, and understanding that we are free to compress and continue to ask a few more questions. Why don't we take this moment to thank our speakers for coming to visit us.